Today, we're gonna go over 2026 AIME question number 8. Let n be the number of positive integer divisors of 17,017 to the 17th power that leave a remainder of 5 upon division of by 12. We're gonna basically find such an n, but I'm gonna find the last 3 digits of this n. So we have the concept review. In the modular arithmetic, we have this property. If A congruent K modular M and A congruent to K modular N, M and N are relative prime. And then we can conclude A congruent K modular M times N. So you see the residue for modular M and modular n are the same as modular mn. This is a very important property for the modular arithmetic. We see example 29 congruent to 2 modular 3, divide by 3, the remainder 2. You can also add a 3, that will be the same as 5 modular 3. 2 plus 3, 5. For 29, divide by 4, the remainder is 1, so 29 congruent to 1 modular 4. This is also congruent to 1 plus 4, which is 5 modular 4. And then we can conclude 29 congruent to 5 modular 12. You can see this one, 5 modular 3. This is 5 modular 4. 3 and 4 are relatively prime. So you're going to get these 5 congruent to 5 modular 12. That's an example describing these concepts about the modular arithmetic property. Now let's take a look at the question solution. 17,017, we can prime factorize it as a 7 times 11 times 13 times 17. And then if I take the power of 17, certainly each of the prime take the 17th power. Any factor of this is in the form m equal to 7 to the a, 11 to the b, 13 to the c, 17 to the d. That will be the factor for this power. A, b, c, d may be 0, may be positive integers. So that is from 0 to 17, can be any value here as a factor of this power. The requirement, m is divided by 12, we want to get the remainder 5, i.e. m congruent to 5 modular 12, translated as the modular language. So now we get this m in this form. M is 5 congruent to 5 modular 12. And then we have to take the modular 12 for each one of these power separately. If we can find m congruent to 5 modular 3, and also m congruent to 5 modular 4, and then we can, using the modular arithmetic property, we can get the result. That means if we can find m congruent to 5 modular 3, at the same time m congruent to 5 modular 4, by the property of the modular arithmetic, we can conclude m congruent to 5 modular 12. From 1, this will be the same as m congruent to -1 modular 3, because you just 5 minus 6, so you get a -1, just 1 less than multiple of 3, 1 less than 6. From the second one, m congruent to 1, because it's going to be 1 more than 4. So this will be clean residue for modular 3 and a 4 Again, m is here. We need a m congruent -1 modulo 3. At the same time, m congruent to 1 modulo 4. If these are satisfied, we can conclude m congruent to 5 modulo 12. We're going to take the modulo 3 and the modulo 4 for m separately. We find out the result. 7, take the modulo 3, they're going to be 1 more than 6, it will be 1 to the 8th power. 11 will be 1 less than 12, multiple 3, -1 to the b. 13 is 1 more than 12, that will be 1 modulo 3. 17 is 1 less than 18, which is multiple of 3, so -1 to the d power. We can simply write as m equal to -1 to the b plus d power, modulo 3. And then we can do the same thing. We can take the modulo 4. So 7 is 1 less than 8, which is -1 modulo 4. 11 is 1 less than 12, which is -1 modulo 4. But 13 is 1 more than 12, so 1 modulo 4. 17 is 1 more than 16, so 1 modulo 4. You can write this -1 to the a power, -1 to the b power, 1 to the c, 1 to the d power. So simplify to be -1 to the a plus b power modulo 4. So far we get this. For m in this power form, 7, 11, 13, 17 power. And in order to reach our goal, we want m to be -1 to the b plus d power modulo 3. We require m also -1 to the a plus b modulo 4. And then we want m is -1 modulo 3. m is congruent to 1 modulo 4. So therefore, b plus d must be odd. A plus b must be even in order for this one to be true. So in that case, b and a must have the same parity because this sum equal to even. B and d must have a different parity because we want a b plus d is odd. A, B, C, D are in 0, 1, all the way to 17, 9 odd and 9 even. So C can be any, because this one, we don't require for the C to be appeared in the power. So C can be any integer. So we have 18 choices. The choice for B also, they are common to both of these sum. We choose the B first. We have 18 choices as well. The choice of A is going to be 9. Why? Because once you choose the B, and then this is the even, if the B is even, A must be even. You have 9 choices. If it is B is odd, we do the same thing. A also have 9 choices. So for choices, D will be the same. Once B is chosen, we want this one to be odd. If a B is even, D must be odd. You have 9 choices. If a B is odd, D must be even. We also have 9 choices. So the total result for this n is going to be 18 times 18 times 9 times 9. We get this n value. So this is the one we're looking for the n. And that being said, we can find out the last 3 digit. When you modulo 1000, you get a 244. And then we get the answer